Hello and welcome to today's webinar, Affordable Terrestrial Scanning in Government Utilities and Construction. My name is Addison. I'm the Executive Director of the World Geospatial Industry Council. We are the only global nonprofit trade association for geospatial and Earth observation companies, and I'll be moderating the event and also hosting the Q&A later in the presentation. Before we get started, we'd like to run a quick poll of the audience to find out where you're from, and what industries and sectors you work in. The poll will pop up on your screen. If not already momentarily, please be sure to fill it in and hit submit. A few housekeeping notes before we get started today. Our goal is to have an interactive event, so please enter your questions into the Q&A space located on the bottom navigation bar of your screen. There's no need to raise your hand, just post all your questions in the Q&A space. Presenters will respond to all the questions at the end of all presentations during the Q&A session and panel discussion. Also, please be sure to participate in any audience polls as they pop up during the presentations. For information about our speakers and for event agenda, click the Resources tab at the bottom of your screen. We also have shared some useful links in the Resources section, which you can access by clicking at any time. This session is being recorded and will be available for download on demand after the event. You will receive an email notifying you when the recording is available. This session is a part of the ongoing GIS and AI for local government compliance reporting and asset management series. We'd like to thank our series sponsors, Terrestrial and Bad Elf, as well as this session's sponsor, Pix4D, for making this educational opportunity available to you. Today's featured speakers are Nick Smilovsky with Bad Elf, Tom Certiera with Pix4D, and Tim Massey with National Grid. I'll let each of them introduce themselves during their presentations. The overview of our session today is that many local governments, utilities, and construction firms struggle to access cost-effective and accurate terrestrial scanning technologies that integrate with existing GIS and CAD workflows and support modern digital twin initiatives. Affordable terrestrial scanning is transforming how government, utilities, and construction professionals capture and work with spatial data. Today, we'll explore practical, cost-effective tools that are reshaping the data collection workflows, digital twin creation, and asset management. By attending today, you will gain a foundational understanding of terrestrial scanning, how it complements GNSS and photogrammetry, and why data accuracy is critical for engineering, planning, and operational success. National Grid segment will showcase how these technologies work in real-world scenarios across AEC, public works, and municipal operations. Whether you're managing infrastructure projects, modernizing utility asset records, or enabling digital twins for government, this session will provide a clear path to adopting affordable, effective terrestrial scanning. So before we get started today, let's take a look at our poll results. And it looks like we're about 2/3 of local government today, a few state government, academia, and industry. And this is unusual, but we're all from the U.S., at least so far. We know others will be joining the call as it goes on. And looks like we're split between land and public administration, a little bit of transportation and EMS, and then public works. Fantastic. So without further ado, let's go ahead and get started. We have as much time as possible later for the discussion and Q&A. I'm pleased to welcome our first speaker, Dr. Nikolas Smilovsky with Bad Elf. Nick, take it away.
Okay, well, thank you so much, Aaron. I really appreciate it. Hopefully everybody can hear me. I'm pretty sure if you cannot hear or see me, we'll hear the voice of God here shortly. So I want to start just by saying thank you for attending today's event. I want to say thank you as a full transparency comment, as one of the sponsors of this event. Say thank you to the other speakers and again to everybody attending. Hopefully you'll learn a little bit today about terrestrial laser scanning, 3D mapping, and I get the privilege to kick it off. So the presentation I've got today is called Finally. dot, dot, dot. 3D mapping made easy the Bad Elf way. If you've been around the geospatial gig for a while, like I have for the past 20 years, 3D mapping is not new. What we're going to be talking today, though, is a pretty new, novel solution, a solution that I'm pretty proud of, that really bridges the gap in so many ways. So why don't we go ahead and jump in? Before we get too much further, I do have one more set of polls. So there's going to be a industry solutions poll that should be popping up on your screen now. And it's going to just ask a couple quick questions, if you could. Do you currently implement a terrestrial scanning solution? Are you interested in implementing a terrestrial scanning solution? If you do have a solution, are you maybe interested in talking to somebody to see if you can maximize said solution? Last but not least, might you need a high accuracy GPS or GNSS to collect field assets? So go ahead and take a few seconds now, fill that out. We'll come back to it in just a minute. We always like to hear about where everybody is on the sessions. So if you've been coming to these asset management webinars for the last little bit, you probably heard of Bad Elf, but if you have not, let me go ahead. We'll start today with who Bad Elf is. Then I'm gonna, I jokingly say why 3D mapping traditionally sucks. And so we're gonna talk a little bit about some of the issues, nuances that 3D scanning and 3D mapping have, normally accosted the industry, but we've got a really neat new solution. So we're gonna show you that new approach today. I'm going to have a quick conversation about accuracies, datums, what I call POB, point of beginning or bust. We'll talk a little bit about how Bad Elf GPS fits right into that, kind of making sure that everything ties together. And I've got a fun ADA compliance case study where we're going to see kind of Bad Elf, Pix4D, and this scanning solution put together for a real world government type of project and for ADA compliance or American Disabilities Act compliance. And I'm just going to leave off with an opportunity that if you are interested, Bad Elf has an enablement team with some really special training programs that could help you get this type of scanning started. So why don't we go ahead and throw the results of the poll up if needed, and I can just see how everybody's breaking down. And while that is happening, I'll go ahead and just keep going. But who is Bad Elf? If you haven't heard of us, there it is. So let's take a pause here. So are you currently implementing a terrestrial scanning solution? About 30% says yes, about 50% says no, about 20% says not sure. So that's a pretty good bell curve, right? So equal distribution, that's good to see. Let's see here. Are you interested? And I guess what I am, are you interested in implementing a solution? Looks to be here. If I aggregate it, you've got about 60%. So more than half of the attendees are interested. Yeah, right now, do you all use GPS for high accuracy data collection, or do you need it? And it looks like about 40% say yes, and about 40% say no. Okay, always fun to know exactly where everybody stands in the industry. So talking of industry, who's Bad Elf? No, we don't sell skateboards. We've been around for about 15 years. We've been creating global positioning systems or GPS receivers during that tenure. We focus traditionally on aviation and marine industries, but since then I've gotten really heavy into GIS, into survey, into public works, and you'll see 3D scanning. We have a very reliable and rugged set of GPS solutions that integrate seamlessly into iOS, Android, and Windows. This is something we're going to touch on a little bit later called BYOD. This is a concept in the industry today called bring your own device. So we'll talk about that. And then, last but not least, Bad Elf, we've got a lot of really great industry professionals on board, and we would encourage you to leverage our team. We're not just a GPS manufacturer of the last 15 years. We really come alongside that GPS and that hardware and implement the full solution, or the full Monty, if you will. We've got our corporate headquarters in Connecticut. I've got our training offices down here in San Antonio, Texas. We are completely supported and fulfilled. Our devices are designed out of Arizona in Scottsdale, and we have some representation in Michigan as well. And actually, a fun fact, this map needs to be updated. We now have some presence in Colorado as well. So that's Bad Elf. So why does 3D mapping kind of traditionally suck? Well, number one, it's high equipment costs. As if you've ever tried to go buy a laser scanner any time recently, or a drone or anything like that, you'll know that you can spend an exorbitant amount of money, an amount of money that, quite frankly, most organizations will not have a budget for. And so you skip the solution because it's so expensive, or it forces you into a scenario where you're having to get a consultant to come out and do that type of work for you. It's a really high-end technology: LiDAR, light detection and ranging, photogrammetry. These are not traditionally simple technologies. So there is a steep learning curve. It could take teams weeks, if not months, if not years, to fully integrate. In a lot of ways, scanning in the past was slow. You would have to make these setups, and you'd kind of traverse in, kind of hopscotching your way into your job site. That is no longer the case. Confusing data processing. If you've ever tried to, process data, it could be difficult, especially when you're collecting thousands of pictures, for photogrammetry, or perhaps you're shooting out thousands of lasers a second and creating a point cloud that's, gigabytes in size. Those gigabyte-sized data sets, this big data, inherently has its own set of headaches. So that was traditionally something that could dissuade people from wanting to do 3D mapping. And integration. How did you get that data that you just collected into your CAD or GIS system? And how do these things all line up? How do you get those dots and lines on your map to be in the right place? Add all of those kind of traditional issues with 3D mapping, plus all the normal issues, like weather. We were just chuckling about how hot it is across the country right now. I don't know about you, but I don't like scanning in 115-degree weather with humidity. So you add in all these traditional kind of quote unquote super professional term here, sucky agents of 3D mapping plus normal stuff, and a lot of people would not get into the industry. And I'm here, and I think you'll see through Tom and Tim's presentations, we are here to convince you that the time is now to implement a new solution. That new solution is literally Pix4D and Bad Elf. Both companies have been around for quite some time. Bad Elf is an affordable, accurate, and versatile BYOD GNSS. And most of you would know that Pix4D is the world's renowned kind of photogrammetry point cloud software for both UAV traditionally and terrestrial scanning. The approach that you're going to see today with Pix4D, Catch, and Bad Elf is what we call the BYOD approach, the bring your own device. What is your own device? It's the cell phone in your pocket, the tablet in your backpack. So with your iPhone, with LTE or cell phone connectivity, with a Bad Elf GPS, with the Bad Elf Flex, with an RTK network, that's a real-time kinematic network, that's a corrections network that provides high accuracy to your GPS, the Bad Elf, and that high accuracy is passed to the Pix4D Catch app on your iPhone or iPad. You add all of those things together with some techno wizardry, which you're going to hear a lot more in a minute from Tom and Tim, and I'm not going to get into that stuff today. That's for my co-presenters. You put a phone with a Bad Elf, with an RTK network, with Pix4D Catch, and you are engineering magic. And you can see in this picture here, the phone and the GPS mounted, and this person is looking actually at a construction site as they're putting in curb and gutter and fill. So I mentioned earlier, I was going to talk quickly about POB or bust, this idea that all geospatial projects need to have a strong geodetic background. So let's talk about this. Traditionally, in the world of surveying, there's a concept called point of beginning, or POB. This is like the rug that ties the room together. In ancient Rome, there was literally a monument in Rome, and all maps led back to that monument. That was a cornerstone or a point of beginning for the entire Roman mapping architecture of the Roman world. Maybe you've heard of Meade, Kansas, or Meade Ranch, Kansas. That was a point of beginning. Or you've been on a construction site and you know that there is a monument there that is a point of beginning, or a 000. The point of the beginning here is not that we have to always set control with what we're doing today, but it's the idea that you want to know what's happening with your geospatialness. Where is it going? Know that all good geospatial projects need good geodetic foundation. You can't build the house or that GIS or CAD unless you've got a solid foundation of spatial accuracy. And we're going to talk more about that today too. I need you to be thinking about coordinate systems and datums. Where are you in the world? Are you using universal transmercator, or perhaps you're using a state plane system? Are you using US survey feet? Are you using meters? Are you using orthometric height, ellipsoidal height? There's some stepping stones that you need to think your way through, or all these really cool data we're going to collect today and show you about are really not going to be worth much. CRUD in is CRUD out. If you have inaccurate geospatial data, you will never be able to have a good digital twin. So talk to me about ground control points, Goose, right? What is a ground control point? Well, you can see in the picture there, those are actually Pix4D ground control points in the middle. On the right-hand side, you see my Bad Elf colleague there setting up a Bad Elf flex on top of a survey control point. And then on the left, you see a kind of fake Bad Elf monument. If you've ever been walking around, these are the types of ground control points. These points control the data. They tie the room together. And this is critical. And this is how Bad Elf and Pix4D make a really good match in heaven. The Bad Elf provides this high accuracy data, this synchronous data, if you will, this synchronous data that's all going to line up and give you a happy digital twin. And as I said, like, how does Bad Elf fit into this picture? Well, we create affordable GPS. We've got our Bad Elf Flex here on the screen. I'm not going to sit here for too long. Suffice to say, this thing is the Swiss Army knife of GPS. It can go fully survey grade, which you're going to need, for a high accuracy scan. You can see here, it uses a helical antenna. It's a little bit of a different form factor. We've got a screen, we've got buttons, we got 12 hours of battery life. We can do base and rover. You can connect peripheral devices like laser scanners, you name it. We've also got the Bad Elf Flex Mini, a smaller device, a near survey grade device. Right? So depending on your needs, if you need something bigger, a little bit more reliable and accurate, you can go down that road, or perhaps a little bit more affordable and versatile and easy to carry. Okay, so Bad Elf, as I mentioned, we create the GPS that ties the room together. Our GPS augments with the Pix4D scanning on your phone or tablet, and then we provide a high accuracy. Okay, so let's take a few minutes. I'm going to watch this video with you all now on ADA compliance. If you've ever been around, GIS, American Disabilities Act, and ADA transition plans have been something pretty big in the state and local government space of the last 10, 15 years. So let's learn, or see at least, how Bad Elf plus Pix4D can be applied to an ADA compliance project. Here we go.
Hi, everybody. Thanks for joining today. I'm Chris the Bad Elf, and I'm here at UTSA in San Antonio, where I'll be conducting an ADA survey using Pix4D Catch and the Bad Elf Flex. We'll be collecting ramps, crosswalks, and other ADA assets, so stick around if you'd like to see all the tips and tricks that go into collecting a quality 3D scan. We're here at one of the ADA ramps we'll be collecting today. Whenever we're scanning it, specifically interested in capturing the running and cross slope so that whenever we generate that point cloud and we get back to the office, we can go ahead and take those slope measurements in an accurate, precise, and repeatable manner. So how do we get started using the solution? First, you want to make sure you're paired with Bluetooth, and then you're going to open up the Pix4D Catch application and engage RTK correction. So to do that, I'm going to go here to the top left. I'm going to click these little three dots and hit RTK via Bluetooth. From there, it's going to recognize the flex. It's going to recognize my GeoNet credentials, and then I'll go ahead and hit connect. So right now we're at about 8.3 inches without RTK corrections. Now we're engaging it, and if you see there, I'm actually getting 0.8 inches of GPS accuracy for my scan. And now I'm going to go ahead and walk this ramp, crosswalk, and other ramp. And I think that wraps up our final scan. So assuming we got everything, let's go ahead and pack up, get to the office, and see how the data came out. We're back in the office, and it's time to start analyzing the point clouds that we created while doing our 3D scans of the ADA ramps at UTSA. To get started with putting this point cloud to work for us inside of GIS, we'll begin by adding annotations. If I click my line, you'll see that I can create cross slope measurements and running slope measurements with a couple clicks of the mouse. From there, I can generate elevation profiles, signify my slope as a percentage, and export to GIS in the form of a shapefile or CAD as a non-proprietary DXF. All right, everybody, we're in ArcGIS Pro now, and the first thing that we're going to do is bring in the shapefiles that we exported from Pix4D Cloud. So to do that, I'm going to add a folder connection by right-clicking here on Folders within the catalog pane. From there, I'm going to navigate to the folder that has my data. Hit OK. Now that I have that folder connection, go ahead and open it up. Select my layer, which is UTSA ramp slopes. Right click it, hit add to new, and create a new map. Now this is going to come in the default base map, so we're going to go ahead and change it to an imagery hybrid. Give us the most situational awareness of the campus. To change the base map, I'll just come up here to the ribbon and change my base map to imagery. And one thing that we can note right away is that we collected this data in a very special location. If we look closely, we can tell that while UTSA has many parking lots, this one is specifically designed and designated for ADA access to the campus. To ensure ADA compliance for these ramps, we'll need to take a look at the slope of each line. The quickest way to do this with the data set this small is just to look through the attribute table. And here we'll see that each of our lines has a slope associated with it. For running slope, we're looking for values under 8%, and for cross, we're looking for values under 1.5%. So we verified that everything is in compliance, and now we can share the data on ArcGIS online, so we can put it in a dashboard, we can share it with decision makers or other departments. First, I'm going to right-click the feature layer, and then I'm going to go to sharing, and from here, share as a web layer. This is going to pipe this in directly to ArcGIS Online in my organization's geodatabase. Now we just hit Analyze, and now we'll just go ahead and hit Publish and share as a web layer. Now anyone within the organization can view this data and make actionable insights. If you've done ADA compliance work for a while, then you're probably very familiar with the typical process. Oftentimes, this data is coming in the form of a spreadsheet with a couple slope measurements and maybe some coordinates, or other times it's only coming in as a marked up aerial photo with stationing. Now, converting that into reliable GIS data takes time, and the accuracy is not always guaranteed. For this project at UTSA, we used Pix4D Catch and the Bad Elf Flex to capture geo-referenced 3D data right in the field. It's accurate, tied to the state plane coordinate system we chose, and it's ready to publish in ArcGIS Online with minimal post-processing. At the end of the day, it's just a faster and more reliable way to document and share these ADA site conditions. That concludes today's video on how Pix4D Catch and the Bad Elf Flex are.
Okay, so hopefully you learned a little bit about how this solution can be used for ADA. You'll see other project examples here shortly. So how do we get there? GET being an acronym in the Bad Elf world for Geospatial Enablement Team. We've got an entire team employed to make you or help you get from zero to hero. Our team provides these custom solutions and trainings and consulting services for all of our customers. We come alongside that hardware and really make sure that you are confidently collecting data as quickly as possible for either saving the world, making money, or whatever reason you're using this 3D data. You'll see that we have several Esri badges and certificates. We're also a GISCI endorsing organization. We're also part of the WGIC, and we're on GSA. We have a very special Pioneer Package learning management system that's been newly launched to wrap around this kind of holistic process of getting the equipment, the solution, learning, and getting off the ground as quickly as possible. You can always reach out to us. We love giving trainings, whether it's to train an entire city or just a one-off person, to let us know. That concludes what I've got today. I probably went a minute or two long. If you are going to be at the Esri Users Conference here in just a few weeks, be sure to swing by the Bad Elf booth. You'll be able to find us and our Bad Elf team there. Maybe keep an eye out for the actual Bad Elf costume as well. So that's a little bit about how this whole solution works. There's a little bit about why accuracy is important, why this is affordable versus, say, old school $150,000, $200,000 scanners. Okay, so I'm going to pass the baton. Our next presenter is Tom, and Tom is with Pix4D. Tom is a registered land surveyor. He's way smarter than I am. So, Tom, if you are around, why don't you take it away? I'm going to stop sharing, and it is all you, my friend.
Hey, thanks, Nick. Let me give my screen a little share here and put this in slideshow mode. There we go. Great. So yeah, thank you everyone for joining. Nick, thanks for teeing everything up here. As Nick said, my name is Tom Sertiera. I am a professional land surveyor in New York and Connecticut. I've been surveying for about 25 years in infrastructure, utilities, transportation, and energy primarily in Northeast New York area. These days, I run customer success over at Pix4D. I'm in charge of training, support, pre-sales consults, and just general consulting here in North and South America. So today we're going to talk about accurate 3D scanning and augmented reality right in the palm of your hand with your cell phone, right? And I'm going to dig a little bit into the technology here. We'll cover the kind of an overview of the solution, a little bit about the technology, no quizzes, I promise. Some big words in here, but no quizzes. And then we'll talk about the accuracies that we can achieve, because that's what everyone always asks. And then we'll talk about some use cases here. So first and foremost, who are we at Pix4D, right? We transform images into accurate 3D models. So we take pixels and turn those into points, right? It's a process called photogrammetry. We're a worldwide company. Our US headquarters is in Denver with our global headquarters and our development teams in Lausanne, Switzerland. We have over 70,000 active users. We were one of the first modern structure for motion photogrammetry companies with a focus on drones back around 2011. 2011 is when we were officially founded, but the technology really came about just around that time. So really, we've been around for a long time, and we really focus on accuracy. We are a science-based company. When I owned my own surveying firm, that's why I picked Pix4D, was because we were the most accurate. Pix4D always provided the best reports and gave me as a surveyor the most confidence that I could to certify these maps and that I was putting out. So our part of the solution here is the app, right? So Pix4D Catch, that's our app. It runs on iOS. And what it is, it's a high accuracy 3D scanning device app for your phone or your tablet. It provides augmented reality visualization of previous scans, of points, design plans, GIS data, annotations, and things like that, CAD data and stuff as well. It has some basic survey point collection for ground control points and tie points and things. And when it's paired with our Pix4D Cloud, it creates a fully automated workflow for collecting the data, processing the data, visualizing data, and analyzing it. So like I said, Pix4D Catch is the mobile app. That's the data capture app portion of the app. We have our Pix4D Cloud, which is our cloud processing and analysis and sharing tool, and Pix4D Matic, which is our desktop processing and analysis tool as well. One thing I wanted to mention here, Nick showed that ADA video, and he was showing the lines and the measurements in ArcGIS, which is really cool. But we can also, through our software here, we can process the data, we can analyze the data, but we can also export all that data into whatever generic format you're looking for, whether it's going to CAD or GIS. So in ArcGIS, we can export the mesh models and as SLPK, scene layer packs, and those are drag and drop of a 3D mesh directly into ArcGIS, into an ArcGIS scene. So it's a really cool way to be able to visualize some of this data in ArcGIS. So let's talk about the technology here a little bit. Right, so we're using a technology called photogrammetry. This is nothing new. It's been around for a very long time. It's a science of taking accurate measurements from physical objects from photos. So take photos and measure from those photos. This technology dates all the way back to Da Vinci, right? He was one of the first people to theorize that this was possible and to start to work it out. Practical techniques were developed by French scientists and geodesists in the 1830s. So I mean, we're going back 200 years now here. As surveyors, we started using it in the 1910s with the USGS aerial surveys. It was used heavily in World War I. But it stayed kind of stagnant. You know, technology advanced, of course, some of the reviewers and the data extraction tools, and it got better. But around 2007, 2008, this technology called structure from motion photogrammetry started to become more popular. And then you combine that with the fact that we're getting low cost drones around that time, the old Phantoms, the custom built things that we used to all mess around with. And then we had really powerful computers too. So we were able to go from taking photos from airplanes and sitting in dark rooms, looking through stereo viewers and picking individual points and drawing lines and things like that to make maps. In there, to being able to take every pixel from a photo and turn that into a three-dimensional point. And that was a really, really big leap. It made this way more accessible to people and provided much richer data because now we're getting true 3D point cloud data from those pixels. And here you can see photos to a 3D model. Terrestrial photogrammetry itself is also not new, right? It's been around for a little while now. It's a little bit different than drone-based photogrammetry or aerial photogrammetry, but it's been around for a while, right? That was the first 3D picture of a president with President Obama there. That was done with photogrammetry. You have those old Trimble units, those rooftop Trimble units with usually pretty low resolution cameras on them, but they could collect some 3D imagery from them. Also very heavily distorted 3D imagery. You have turntable stuff down there in the lower right to model objects. It's actually how I discovered some of this stuff, was random coming across that kind of stuff randomly. Down there, that bike trailer is actually a rig I built once. I had my survey firm, was trying to compete with some of the bigger firms, and I couldn't afford a mobile mapping unit. And I built my own using a bunch of GoPros. I put my GPS in the middle of it. It worked. It worked very well. I wouldn't say that it was practical, but it worked quite well, right? So photogrammetry works with just about any type of camera. As long as we know the parameters of that camera, such as the focal length and the sensor sizes and things like that, we can turn pixels into points. But now we have these cameras in our pockets every day. We're all walking around with these cameras in our pockets, and they're really good cameras. I really want to stress that. These cameras are really high quality, right? 8, 12 megapixel cameras. And of course they can go higher than that, but Apple limits us a little bit on that. And you don't really want a 65 meg photo to be processing either. But these cameras are really good. I wish I had these cameras when I started drone mapping, especially when we're really close to the object. You know, we're 15, 20 feet, 10 feet away from the object here. So we have very good cameras on these phones that we're carrying around in our pockets all the time. A fair amount of them now also have LiDAR on them, and we'll talk about that in a minute, but it is a useful technology. It's an iPhone LiDAR. It's not a full 3D scanning, professional, you know, Leica or Trimble or Faro type of LiDAR, but it's really useful, right? One of the most intriguing things here is, though, is that we get the use of ARKit, right? And ARKit is Apple's augmented reality software development kit. And what that does is it gives us another way to position the phone. It gives us more information about orientation and position on that phone. And we can use that in our calculations for geolocation. And it provides a number of advantages. So ARKit, and this is, no one has to memorize this. Like I said, no quizzes here. It's a mouthful. I realize that. The technology behind it is something called visual inertial odometry. Really what it is a computer vision technique to determine the position and orientation of a device using camera images and inertial measurements, because your phones have IMU units in them, relative to a local starting position. And that's really important, relative to a local starting position. Nick talked about POB, and we'll talk about that in a second here. So it's a visual positioning system that's used by Apple, it's used by Google, it's used by Niantic, it's used by Esri, it's used by a lot of different people that helps you determine, again, the position and the orientation of the device relative to a local starting position. Here's a short video where you can kind of see illustration of the phone capturing points. So those are tie points. Those are common tie points between images that it's capturing right there. And that's how it's able to know where it is in relation to those objects. Just like in augmented reality, right? If you put an object in the middle of a room, you've seen the videos, you put an object in the middle of a room, you can walk around it and it stays there. It's because the phone knows very precisely where it is now compared to where it just was. But that technology is prone to drift. It's really useful, right? You can use it well, you can do scans of small areas just fine, but it's prone to drift. And if you want to, one, have good, accurate geolocation, and you want to have maintain that accuracy and that good geolocation over longer distances, we have to pair that with RTK GNSS. And Nick talked quite a bit about that. That is real-time kinematics, as a correction service that is broadcast to the GNSS device. And that can take that down to, a centimeter, 2 centimeters in accuracy in good conditions. So by pairing that great camera that we had, that LiDAR unit that we had, all of that AR kit technology using the odometry, we take all of that and we pair that with RTK GNSS, and now we get a good initial position. Remember, I was talking about initial positions before for that odometry. Nick was talking about POBs. This gives us that POB, gives us that initial position of where we start, right? Very good at coordinates. It continues to give us accurate image geolocation as we walk around doing our scan. And it allows us to maintain accuracy over longer distances, right? That odometry is prone to drift over time. The RTK constantly corrects that odometry. In that Pix4D, we actually take all of that information inside our app, Pix4D Catch. We take all that information, the visual odometry information, the sensor data from the phone, the GNSS data from the Bad Elf here, and we put that all into our own algorithm, which we call GeoFusion. And that's how we come up with the location of each photo that is taken for the photogrammetry. What's interesting about that is that by using all of that data, we can weight those different sources of information very precisely. So if you're walking with RTK and you have very good accuracies and you walk underneath the bridge, your accuracies are going to plummet because you can't see the satellites in the sky, right? So then we look at that and we say, oh, wow, the GPS or GNSS accuracy is really low. Now we're going to rely a little bit more on that odometry stuff. Then when we come out the other side of the bridge, we're going to get that RTK accuracy back, and now the whole thing's going to snap to that. So we can maintain accuracy even in places where GPS and GNSS don't work traditionally, because we can use all of this other technology to position these phones. So the LiDAR, this is such an interesting topic, right? There's so many scanning apps out there that just use iPhone LiDAR. And in my opinion, iPhone LiDAR is, I wouldn't expect great results with just LiDAR in today's phones. I can't promise you that's not going to change. I hope that changes. But right now, there's a lot of limitations, right? You have a really short range, 10 to 15 feet. Point cloud's usually not as dense. Point cloud can be noisy here. But it still creates useful data. Like I said, it's really cool. It's really important. We use it in the calibration. When we do the photogrammetry calibration here, we can use that as checks to create scale and help us out and make sure that the photogrammetry calibration is proper scale and accuracy. And another cool use case for it is that it fills holes where photogrammetry fails. Photogrammetry tends to fail on matte, smooth objects or shiny car doors, right? The technology is used a lot by police for accident reconstruction. So on those shiny car doors, photogrammetry sometimes fails there. We have algorithms in our software that look for those holes. And if we have good LiDAR data, then we'll supplement it with the LiDAR data. It's not going to be as dense or maybe as accurate as the point cloud data, but it will fill those areas in and give you some information in those areas. So it's the LiDAR, I personally would not really trust it on its own for scanning. I think maybe small objects, real close, maybe for something like that. But from an accuracy perspective, I don't really trust it on its own. But it is still very, very useful for us in the overall process. Here's a couple good examples, right? On the left, you can see a LiDAR-only point cloud. On the right, you can see the photogrammetry only point cloud. Down there, just underneath that manhole, you can see there's some squares. There's a benchmark right there. You can barely see that in a LiDAR only. In this one here, this is a bridge. We're doing a little bridge work out here. Again, huge difference here. LiDAR only on the left and photogrammetry only on the right. I mean, you can see the roots and twigs and rust flakes just from the photogrammetry and the point cloud right there. So I hope that's an overview of the technology. I mean, a 10,000-foot overview. There's a lot more we can talk about, and I can certainly spend hours going into this with anyone if they'd like, but we don't have that time today. So let's talk about the accuracy of this system, because this is what everyone always wants to know. How accurate is the system? And I've gotten really good at my LinkedIn posts these days because people really love to challenge me on LinkedIn when I post anything accuracy. So I like to cross my T's and dot my I's when I do accuracy testing these days. And I also make all of my data available publicly. So if someone wants to question any of it, I'll give you everything down to the raw GNSS logs. On the topic of accuracy, we have to think about it in two ways. There's two types of accuracy. They're both very important, but you don't always need both. Absolute accuracy is really what it comes down to. It's the position of your model or your scan on the Earth. It's the accuracy of your position on the Earth, right? It's tied, it's the accuracy to a coordinate reference frame or a certain reference frame, a coordinate system technically, but it's really the accuracy of your location on the Earth. Relative accuracy, on the other hand, is the accuracy of a measurement on your model. So if you put a ruler down on that model of 1 meter and you measure it, that's your relative accuracy right there, right? So they're two different types, and they do go hand in hand, but you don't always need both. Bridge inspectors, for example, tend to really just focus on the relative accuracy of what they're doing because they're working underneath bridges. They just need to measure things on that bridge structure itself rather than where it is on the Earth. A lot of times they don't care. So you have to make sure you decide what matters to you. Do I care where this is on the Earth? Or do I only care how accurate the model is itself? So let's talk about absolute accuracy here. So this is a test I did. I did this one a couple years ago now, and I had 85 checkpoints spread over about 1,200 feet. It was connected to a New York State RTK network. Base station is about 3.5 miles away. And with no control, with holding no control on it, just using the RTK, the scan had a vertical accuracy of 2.5 centimeters there, sub-tenth, right? And when I added in a little bit of control, you can see we got down to 1.6 centimeters. That was with only 4 control points along that 1,200-foot thing. So I think that's pretty good from a cell phone, if you ask me. So this is testing vertical. If we want to look at horizontal, I recently presented at GeoWeek for ASPRS and the American Society of Professional Remote Sensing, and their standard, I think I got that right, and their standard, which is used for drone mapping, aerial mapping, LiDAR data, and so on. So here I had 35 checkpoints spread out over 800 feet, again connected to that same NiceNet RTK network. I took 4 scans of this, right? And you can see on this, when I averaged all those scans together, we were about 4 centimeters in horizontal accuracy, and we were 1.6 centimeters in vertical. And I get challenged a lot. I think this is pretty amazing, again, from a cell phone. I get challenged a fair amount on why is the vertical accuracy better than a horizontal accuracy? Because in standard GNSS, GPS work, it's usually the flip-flop the other way. Horizontal is a little bit more accurate than the vertical. But because the elevation of the models we're taking is essentially an average of the elevations of all of those photos that we took along that scan, the error kind of works itself out. It kind of averages itself out in the vertical here. So the overall scans, vertical accuracies can be very, very tight because of the way we average out the elevations of each individual photo. So here again, 35 checkpoints spread over 800 feet, a rigorous statistical analysis of all of that data. about 4 centimeters in horizontal, and that's mostly caused by that last one there. And 1.6 centimeters in the vertical here as far as accuracy of the system. Relative accuracy, right, really comes down to point spacing at this level, or your GSD, if ground sampling distance from the drone world. So here again, for some bridge stuff, just slapped a ruler up on that bridge, and we did some measurements on it. Checked it in Pix4D Cloud and in Pix4D Madican Survey, and you can see it's dead on. This was done without even being connected to RTK. This was done just scanning with the phone, because again, we're only concerned about that relative accuracy here. So we are dead on the scale of our models here, and the relative accuracy of our models. These are just show off slides here. These are actually mesh models from that scan. These are not photographs. These are actually mesh models from the scans that we did. You can measure rust flakes in millimeters on these if you wanted. Just another quick relative accuracy one here of some anchor bolts. And again, another, but these are mesh models. You can see the grain in that wood. You can count the threads on those bolts if you want. In fact, we actually did some of that with Tim on some gas valves when we were doing some demonstrations with him maybe a year or so ago, which worked out pretty well. Augmented reality accuracy. So over on the right, I have a rebar, some property corners I found out there. There's some challenges to measuring the accuracy of augmented reality. One, it's constantly updating as you're moving around, so it does move around a little bit. It's a virtual visual representation on the screen that you're looking at, so there's some interpretation that's open to it. It does improve over time. Objects closer are more accurate than objects further away. And traditional GNSS, of course, RTK things doesn't work under bridges, right? Let's factor in on this. So I did an experiment. I went out, I made these targets with these rings on them. They're 1/10 intervals. Did some RTK observations on those, loaded them into Pix4D Catch, and then went out and viewed those in augmented reality to see how close they got. Here we go, see if the video plays. So my observations on this are that all the targets I tested got within 0.2 of a foot, about 6 centimeters, within seconds of arriving on the point. They got a little bit better when I stayed on that point and watched it for a little while, got down to that 10th range or 1500th range. Once it was locked, it usually stayed as long as I kept walking around it and was looking at it. It stayed pretty tight. But I did find a couple little outliers here and there. So in general, when people say, what's the accuracy of the augmented reality these days, I say anywhere between 5 and 10 centimeters is generally what I'm finding as far as accuracy goes. But you can see it snaps right in there as you get close to those in the augmented reality. This was just one more fun one. I was up on a local mountain here in New York, and I knew there were some property corners out there because I'd surveyed it. So I entered those coordinates in and went out there in the woods. So I was underneath trees, did not have good GNSS by any sense of the word. I was in RTK float this whole time, and I was still able to get within about a foot of that pin out there in the middle of the woods on the side of a mountain, which I was pretty happy with. It's good for recon and things like that. Think about finding water valves off the street, off the side of the road or things like that out there. So where does all this stuff hit the road, right? Where does this actually, how do you use all this stuff? It's really cool technology, really cool stuff, but how do you use it in the real world out here? So the biggest one that we have right now is utilities. This is huge for us. Utility markout mapping. I have projects where I've gone out and mapped utility markouts on a 2 or 3 lane road, completely from the side of the road. Never had to go out into the road. Just walked up one side of the road and walked back the other side of the road scanning. Took me about 5 minutes to scan the whole thing. I uploaded it to our Pix4D cloud. When I got back to the office, it was all processed, and it took me about 5 minutes to trace all those markouts out. So 15 minutes of actual work out there to get to CAD files of all the utilities. And I can export those out as DXF files or shape files to CAD or GIS very, very easily. On the right here, we have what I love to call these things spaghetti trenches, right? We're near New York City. It's nuts down there. I'm sure Tim will show you or talk about some of that. trying to locate this traditionally with GNSS or total station 1 is going to take a very long time. It's really prone to error. There's a lot of stuff going on here, and you have to shoot this exactly right to get it to come in properly. You can scan this in 3 minutes walking around this, and you have a real visual model representation of all of these utilities that you can then utilize. It really reduces the amount of error in utility locating and mapping. The augmented reality stuff here, this is, I went out and scanned this the day before they did the saw cut, when they did the saw cut, and then I went out there the day they did the excavation. So you can see the saw cut, you can see the markouts, and then you can see the actual excavation there. The excavator and the building inspector there hanging around in the back. And we're right on top of those things. So you can visualize anything that you've scanned previously in the ground. And then right here, these are some utility markouts. So these, I scanned these almost 3 years ago. I apologize for the potato quality of this video. I don't know what happened here, but I scanned these about maybe 3 years ago, almost, these utilities. And right now we're looking at the scan of those. And I'm going to turn that scan off and I'm going to leave the lines here. Right now we're looking at all those, it's all been paved over. There's no markouts there anymore. And we're looking at those utility lines exactly where they were on the ground at the time I did that scan 3 years ago out there. And then this one right here, this is a little bit of a different use case. This is out in Connecticut with Connecticut DOT, and we took an IFC model of their bridge design. This came from Open Bridge Designer from Bentley, and we put that into augmented reality so they could come out and see where the new abutments are going to be. You can see where the footings are. You can see the girders. You can see everything you need to out there on this one. Construction inspection is another huge case. Pay items, volumes. We can do volumes in the field on these. So you can just scan a pile in a field, hit compute. It's going to tell you the volume of that pile. So you can check your dump trucks, to check the tickets, make sure they're coming in right. Pay items on the walls, as-built for utilities or footings or anything that's about to be buried. Put this stuff in the hand of the construction inspector out there. We're working with multiple DOTs across the country right now who are using this system quite heavily. And then more just general inspection. I showed that bridge model. We can measure the rust flakes on that, right? On the right-hand side, we have a Frankenstein column, they called it, and it was a bad concrete pour. So we were able to scan this, draft out where all the rebar was in it, and then they were able to design new hooks into that rebar so they could repair this structure here. And then supplemental scanning. If you're using drones already, they can't get underneath bridges. They can't get underneath eaves, right? Here on the right, we use some stuff. This is for Massachusetts DOT, where they had a great scan of this whole area. And then we went in with the, and with Pix4D catch, and we're able to get underneath those bridges and add those piers and abutments in. So that about does it for me on here. I hope these use cases, I hope the technology made some sense to you guys. I always feel it's a little bit important. Maybe it's just because I'm a surveyor here, but I like to understand and have some sense of the technology I'm using, right? Don't want it to just be black box voodoo out there, right? Yeah, it's this accurate. Prove it, right? And that's what we do here at Pix4D. We focus on accuracy and we focus on quality. So with that, I'm going to invite a good friend of mine, Tim Massey from National Grid, to come in and join. And Tim's working on some really interesting projects. I'll let him introduce himself. He's working on some really interesting projects down in the New York City area and on Long Island using Pix4D Catch and ArcGIS. So Tim, take it away, man.
Thank you very much, Tom. I appreciate that. And as Tom mentioned, I got invited to speak today because I'm a guy who's got a lot of problems. I have lots of problems. Thankfully, as a land surveyor, most of those problems are spatial. But like a lot of you, we have to deal with old records, new records, things getting done today, things that were supposed to be done tomorrow. A lot of that information and a lot of that data, well, what do we do with it? So what we'll share today is taking a little bit of what both Nick and Tom spoke about and really showing you how we've taken that and actually made use of it. So let's bring up what I have here. We'll share my presentation. So presentation going to be named Reimagining Survey As-Builts. So you're going to hear a little bit about what I do. So I work at National Grid in the downstate region, covering most of Long Island and New York City. As the land surveyor, we're covering the gas installation, construction, and design process from end to end. We're there with every team along the way. And one of those things that we do is collect our information as the pipes go in the ground. And as a surveyor, we said, hey, we have a lot of information. What can we do better with it? So you're going to learn a little bit about what I do, and then a little bit about how that may be able to be reflected in what you do. So getting right into it, we put in gas main. That's what we do. We make sure that New York stays warm. And has power, right? That we can put all those burners on and we can run all those power stations. But when we put in gas main, we don't just locate our gas main. What you're seeing on the screen is a little bit about what we encounter when we start opening up the ground in Long Island and New York. So part of our compliance, and a lot of this is about compliance, right, is we need to ensure that we locate all of the assets that we install. And we also want to locate all of the assets that are nearby our installations. On the screen, every one of these call out boxes is something we locate. Right now, we're locating those things conventionally with a total station and a surveyor on site. So as these projects are happening, we have every day a surveyor on site locating all of the information that's being installed that day. And as you can see, there's a lot here. Like we mentioned, we have gas main, we have our stuff, and then we have other stuff, sewer mains, water mains, and the like. So when we take all that information, our traditional deliverable looks a little something like this. Now, I don't care how long you've been engineering or what you've been up to. If you're looking at this, it's real hard to understand. It's real hard to see. There's a lot of information and none of it intuitively makes sense. And I'll even give you a zoomed in version of it, which is a little blurry, but it still doesn't make a whole lot of sense if you're looking at this. And what you're seeing on the screen is all the information we're capturing. But all that information, if you see all the call out boxes in the lower right, all of that information ties back to an entire spreadsheet full of other information. And this is just the information we're collecting as surveyors. So as you might notice, there's fittings, there's pipes, there's welds. We need to know where every one of those are, and we need to know the other information that goes along with it. So not only are we collecting this information, but there's other teams alongside of us that are collecting information on these pipes, on these welds. And right now, we're creating PDFs and handing them off to folks. So there has to be a better way, right? And so how do we add value to something we're already doing? We're out there every day spending our sweat, time, and hours to create, to locate all of this information. So what do? We said we need to have a better system. So we set out to create a GIS. GIS wasn't created to just show where things were, but it was created to allow people to make decisions quickly. That's it. So you'll notice that this GIS that you see here, if you have some familiarity, it doesn't look exactly like what everybody else has. Your traditional GIS is going to look a lot of points and dots with not a lot of context behind it. One of the key features in our development that we did is ensuring that we had the geometry of the pipe underlaid behind that GIS, behind the points and lines, so that folks could quickly zoom to what it is they were looking for, find that valve, find that purge. Very similar to what any of us would be looking for, whether it was a bus stop or a valve or manhole cover. We all need to find that information. And now all that information, plus what is included in the spreadsheets themselves, is located right here and searchable. We now have all that information available to us in real time. So one of the things that we speak about, and I know I have some of my colleagues from asset management on, and I can't be happier for them to be here because they really pushed development for this. Because what you're seeing now is a project that we did quite some time back, where because we are, as surveyors, had our standards in place, we're able to take older projects and bring them into this same system, so that as our asset management team kind of has the terminology for it, is we're creating a visual digital file cabinet. Teams have paperwork and binders full of information for all of these dots on the screen. But how do you find it? If you don't have that file, if you don't have that folder number and that photo number and that and the actual report, all with the corresponding file names, how are you ever going to find that information? This is how we start to add value to say, hey, we've collected this spatially. Let's start storing some of these things here. So now we have this. We've created somewhere to store the conventional stuff. And this is where it starts to get exciting, because up until this point, we're making digital what we've already done before. We've done it for years and years and years. As-built surveying is pretty much the same, but now we're just representing it differently. Now we've added value to our project managers, our engineers, and have the ability to see this stuff visually and digitally now. But the world's changing, as you saw in the beginning of this presentation. We are also utilizing the same information and getting out there to sites and utilizing Pix4D, as Tom mentioned earlier. We're having success. Early success was, hey, can we get out there and visualize a site so our engineering team can understand what we're looking at? Right off the bat, I mean, we see it here on the screen. The ability to view a job site from your desktop is a game changer. And having the ability to have folks make decisions based upon what they saw from someone scanning has become a huge benefit for conversations in our team. The ability to scroll through a 3D image while you're having a conversation with an engineering team has become invaluable. And I say invaluable, but I'll show you real value. So we mentioned we locate all of that piping, and all of that piping has lettering on it. All of it has its own serial numbers and all its different information, and that's all that information we have to track still, right? Well, what happens if we don't track it correctly? The information we're collecting now is allowing us, this is where we're saving money. We have these units and we need that information for our spreadsheets that perpetuate. If we don't have that information, guess what we do? We have to redig that hole. But now we have the ability to go into these sites after the fact, after we've come back and created a drawing, and we're not really sure if the clerical error was on the weld inspector, the surveyor, or the note taker. But guess what? Now we have the ability to actually jump into these projects and see where those changes have happened. So the cost of technology for these units, we've seen the ability for these units to pay for themselves with avoiding one mistake. The ability to allow us to not make one dig pays for a unit for a full year for us. And that's one of those big pieces for a Pix4D side. And now we talk about some of the other use cases, and Tom mentioned utility markout. As a gas utility, we do a ton of it. And I need to know where things are when I'm putting things in the ground. And one of the things we also do is we also utilize our drones. So what you'll see on the next clip here is actually one of our power stations. Recently, we needed to get some utility information. So we flew a portion of this site with our drone and ran it through our Pix4D. And you'll actually see here, this is the ortho mosaic that was created. And you can see that it's a little faint in the coloring, but you can actually see the utility markout is sitting in here. And as we pop into the 3D model, tying into what Tom was speaking about with both the relative and absolute accuracy, we've seen very similar results. And what allows us to do is to go in and fly our site. And I'm going to play this for us one more time. We're going and fly our site to get the full picture. And we come in and we're able to, like we mentioned, we're able to see this thing in 3D. We have the full picture. We know what it looks like today. But the real value comes in when we're able to go back out on site and not send a survey crew to go and locate that very same markout when it gets updated. And what you're seeing here is a little bit of that 3D model of updated utility markout on that exact same site. And you'll kind of notice as we back out, you'll shift back and you'll notice it's that same intersection we just looked at. So really the versatility and the ability to change the way that we are collecting data and the different means and methods has allowed us the ability to capture more of that geospatial data that we just weren't doing before. And now we have the ability to actually do something with it. And I think that's the biggest piece here for everyone to take away is what is it that we are actually doing with our data? Because we were surveyors. We weren't GIS professionals. We weren't a whole number of things. We're surveyors who just said, we have beautiful data. How do we make it available to more folks? And that's the world we're living in today with GIS. And the big piece to think about is with your data, with what you're doing out there today and what everyone showed you today and the ability to acquire that data, how can you make it more retrievable, more accessible, and really simplify it? And that's really my message for today. I know we're going to have hopefully have a lot of questions. So I'd invite some of my presenters back on stage and let's see if we can get Aaron. You want to run us through a little Q&A?
All right. Great work, guys. Lot to unpack there, and some of the questions have already come in chat. So let's get started with those if we can. Joe asked, what's the cost for a complete Flex hardware setup and software to support E57 and LAS? Can the Flex use any RTA correction service, or is it limited to specific services?
Yeah, I can start there, Aaron. Thanks again for moderating the QC. Let's try that again. Moderating the quality control, right? No questions. Try again. No. So the cost question is, if you are interested, please reach out to Bad Elf. We'll also be doing some follow-up on this webinar. But let's just say, depending on what flavor Baskin Robbins, of ice cream you pick, you're in that $5,000 to $10,000 range. So you're a sub $10,000 unit, which if you were to probably go look for the most affordable laser scanner on the market, you're not going to be under 10,000 without having to Frankenstein something. But again, reach out to us. We could talk a little more specific on what that actual setup looks like for you, which can be a little bit different depending on your needs. I'll also say the Bad Elf Flex can utilize any public RTK network. So we work, most states in the union have public RTK networks. And depending if you can get access to that where you are in the world, you normally can use that. Most paid networks we can also utilize as long as they're open for public consumption. Now you mentioned LAS and some other file format types. I guess I wanted to maybe hand it over to Tom. Tom, could you maybe talk a little bit more about the data coming out of the Pix solution with the help of Bad Elf?
Yeah, absolutely. So Pix4D in our cloud and our desktop software, we can export LAS and LAZ files as far as point clouds go. Not E57 at the moment. Traditionally a little bit more for your traditional static laser scanner stuff, but LAS, LAZ. On top of that, we also support, like I said, the mesh formats and SLPK, your standard OBJ files. but really, it's cool to bring that stuff over. It's really good for visualization. Tim showed a lot of really cool visualization. I think that's great data to have. Those SLPK files are pretty light, actually, and these are usually pretty small scans. But you can also, in Pix4D, you can just vectorize some of this stuff. We can draw lines, you can draw 3D lines, you can draw areas, you can draw, circles, all sorts of stuff, points and things like that. And you can export all that data to CAD, to GIS and DXF files, shape files, CSV files. So we really focus on getting that data from our system. We know that's a challenge, right? Getting the data from, you get this big, beautiful point cloud, right? And it looks awesome, but what do you do with that data? Right? How do you get that into your CAD? You can't load that into Civil 3D, right? You can't load that into Bentley. I mean, I know Civil 3D's gotten a little better with point clouds, but I mean, it's still a little bit of torture. So by vectorizing that data, you create much lighter weight deliverables that can then be put out to CAD and GIS. But I still love bringing those SLPK meshes into ArcGIS. It's just drag and drop, and they look so good when you bring them into a scene. So
Yeah. No, thanks. Thanks, Tom. I think that's a great point. I know, sometimes I hear people say things like, I want LiDAR data, but what they really want is some derivative of that, right? They want better
right.
contours, or they want a mesh, or they want something. And to your point, you try to load some of those raw data files onto a laptop, and you're going to be rebooting it pretty soon. Uh, okay, our next question comes from Mohammed around GNSS and loss of signal. Sort of what happens in that scenario? Do you rely on the phone's IMU, or just on the detected features for localization? Anybody want to tackle that?
Yeah, I think that's firmly in our territory here. I mean, maybe Nick's got something in it, but I think as far as the scan and stuff goes, when we lose GNSS signal, we lose RTK fix, right? We fall back onto that odometry, the AR kit stuff, right? The visual odometry. So yes, it is using the IMU, and it's using the features for location, and it's using whatever data we can get to get that location. Like I said, the phone knows very precisely where it is now versus where it just was. It's not really a set amount that you can, I can't say, yeah, it'll be good for 100 feet, right? I don't know. It varies a lot on a scene. If there's lots of features, it's going to go longer. If it's a pretty bland scene, it's going to lose tracking earlier. But we weight all of that data and we tell you the accuracies of all of that data. And as soon as you come out from the other side of that bridge, and you get RTK fix again, it corrects it all back to that when we run the GeoFusion algorithm. So I tell people, I like to start and finish with an RTK fix when I can. If I'm not gonna, I minimum want to start with an RTK fix because we need that POB, right, Nick? So yeah, I like to at least start with an RTK fix. And if I finish sometimes in a little bit of float, I'll usually at least want to check that data, but often it's okay.
Yeah, and I'm going to quickly jump into Tom just to add to everything he just said. Um, when you use Pix4D catch and you're in the process of kind of processing the data, whether it's through cloud or Matic, you get to see a trajectory line, and
Yes.
it shows you how good it is. And so if you find really bad areas, you can maybe go back and start mitigating that. But it's a great sanity check to see, as Tom was sort of saying, if you're an RTK float under the bridge. The other thing I would say is we briefly mentioned it earlier in the presentation, but we didn't really talk about it a lot today. But I bet you, and I might softball this for Tim, in the world of drones, ground control has been used for like the last 100
Yes.
years. We got a history lesson earlier. And in scenarios where you're under a bridge or even in a building, right, you can start to use, ground control targets and tie that data to those control targets, and that's another great way to sort of stamp it all together, especially if you lose that RTK value. I don't know, Tim, do you have any thoughts
Oh
with
yeah, you're right in my wheelhouse because we just did this. Actually, the power station I just showed on the screen, we did the exact same thing. We flew with the drone, we did it with Pix4D, and we did ground control points. And it's just exactly the same way. As a surveyor, we're always going to do those ground control points because that's how we know that you can trust our data. But I'll tell you, we came back and between the catch unit, the drone, and what we did with our traditional survey work on a site that we have tied down real tight, we were within a tenth of absolute accuracy. You know,
Yeah.
we had a little float on one end. We were a tenth high on one end and a tenth low on the other. You know, after we balanced everything. But I mean, at the end of the day, for the size and scale of work that we did that day, we mapped a quarter mile of a power station. So you know, it was pretty impressive to see how quickly we were able to do that when we also mapped that area conventionally, and it's weeks of work, weeks of work.
Yeah.
Yeah.
Yeah, a lot of time savings. And just to, Nick, thanks for bringing that up. And everything is controllable. These are controllable from a survey perspective, right? We have RTK, we're using that, but everything is still controllable. If you have survey control, if you have local coordinates, if you have this or that, we can tie into all of that stuff. And even after the fact, right? Sometimes you go out and you scan and you bring it in and you go, we're really pushing the limits that day. There's a lot of trees around and maybe you find it's not as accurate as you want. You can go back out there and you can find just something that's in the scene that you can locate. And control doesn't have to be a target. It's better if it's a target, but it doesn't have to be a target. I mean, I've used pebbles that I've seen in the same scene before, right? Control can be just about anything. I tell people if you're not using targets or anything, I like to even just spray paint a couple paint dots around your area, and you can go back and locate those if you really need to. It just gives you some extra quality control on it.
All right. Thanks, guys. Yeah, I smiled when you said check in the beginning of the day and the end of the day. That's spoken like a true surveyor, Tom.
Yeah, that's right.
I remember when we would go in the field, we'd have to go find a control point to start the day. Yeah.
Mm-hmm.
Yeah.
No, perfect. Yeah, I think the question around loss of signal can also, the bridge example is great, but I think also, I think you showed the spaghetti utility sort of scenario underground, and I know in dense urban areas with buildings and so forth, you have a lot of obstructions, and you can get loss of signal and data shadows and things like that
Yeah, I'll
in
share
those cases.
if you want. I'll share. I have a really novel method that a utility in New York City uses for this. Not Tim, the other one. They have really accurate aerial mapping of the entire city, and they fly it every couple of years. And they have all the curbs are mapped, so they use the curb returns as their control points in those urban things, or they have manholes and valves that they know the positions of, and as long as they include those in the scan, they can then use those as control.
Perfect.
And
Uh,
even
yeah, go
to
ahead.
add on that, one of the things that we're doing is dealing a lot in downtown Brooklyn. We run into those urban canyon situations, and while we as surveyors can go out there and see a site and mitigate the situation, our goal for handing these terrestrial phones is so that we don't have to have someone who knows how to mitigate that. And what we've found success in doing is getting out ahead of a project, setting 2 or 3 ground control points in or around an excavation. And when the lesser trained individual running the scanner or the Pix4D unit captures that information in there, even if we had no RTK at that point, we're still able to come back and actually control those pieces. So, it's a very cool unit to be able to grab the relative accuracy. And when you have, as a surveyor, when you have those moments where you need to really dial in that absolute, there are those means and methods that kind of harken back to how we do things traditionally.
There's always a way.
Yeah.
Uh, well, I'm being mindful of time here, and one of the things that I run into quite a lot in my line of work is that uh, people will attend a webinar like this oftentimes, and they'll sit and they'll watch the presentation, but they may have this sort of sense that that's all great, but it can't possibly be for me. It feels a bit out of reach, even though they may see the value, they may understand that. What's, and they're like, or what project, what's like if I could only use this on one project this year, what would it be? I was wondering if maybe as we sort of start to close out here, if each of you could offer some thoughts around those ideas and help people really see themselves in these solutions and not just say, hey, that was a webinar that I attended that somebody else was doing the thing.
Anybody
Yeah.
want to go first?
Yeah, sure. Um, for me, like one of the biggest use cases is utility mapping. Whether it's mapping, I mean, this is what we're talking about, but that's on purpose, right? Because the ability to capture whether it's markouts or whether it's a pipe in the ground accurately, and being able to, like Tim showed, going to reference that data again in the future is super helpful. The first job I ever did with a drone, they ripped up a fiber line the first day on construction and sued me as a surveyor. And they were like, we got the tickets, it was marked out. I was like, I got a drone photo that shows it wasn't. So, take it for what it is. But also look at the standards that are happening. ASCE has a 7522 utility as-built standard, which is starting to get adopted by DOTs and municipalities and stuff around. And that calls for creating 3D representations of your utilities in it. So I think one of the most exciting spaces for me is utilities and just the safety and cost saving side of it. I mean, I mapped a 350-acre site in the morning, and by 3 days later, we had traced all the utilities on it. It took them 6 weeks to map it, to mark it out. So it's, big cost savings there.
Tim, you want to go? We can go inverted. That'll go last. How about
Yeah,
that?
sure.
Oh.
I think, Tom hits a great point, and really was the origin of why we started utilizing the Pix4D was we used to spend I used to send out a survey, a subsurface utility crew to go do markout. It cost me $3,000 to send them out there to do a full day's worth of work. And in order for me to have that information digitally, I had to send a survey crew out there the following day for another $3,000 to pick up that information. On 2 jobs, you can pay that off and effectively turn my subsurface utility contractors into delivering me digital deliverables. Now have the ability to take that information and bring that directly into CAD. No longer are my subsurface vendors in there going into Google Earth and doing the same thing, redrawing all the lines, but just not spatially accurate. Now we have that information readily available and have our subsurface utility contractors responsible and accountable for the work that they've done as a whole, rather than handing that off to a whole nother group. So really that opportunity cost of, what happens when something goes wrong, the cost to get in here to see what, between the Bad Elf unit and the Pix4D, if you can answer 1 or 2 questions a year, you've pretty much paid that thing off. I think it's a real compelling argument for, answering those questions that aren't easy to answer.
Yeah, I think that's a key point, sort of that fit for purpose idea, the, right tool, right solution for the job.
I like
Bring us
that.
home, Nick.
All right, let's see what I can do. All right, I mentioned, so the question was, how would you jump into something like this if you've always said, maybe that's just, it can't be for my org or for me? I mentioned earlier the concept of bring your own device. So question 1, do you have a cell phone or a tablet, right? If you have a cell phone in your pocket, which I'm guessing you do, there's a good chance that it probably 50% or more, you have iOS. So if you have an iPhone in your pocket today, right now, go into the App Store, download Pix4D Catch. You could download the app right now, and you can get a trial for free. And then you're going to stand up from your desk, and you're going to scan your bedroom, your room, your office. Don't care. Go outside, scan your curb of the front of your building. Start using the free version right away. And what you'll see is you can start accessing cloud, and really quickly within, that first week, you've got real actionable data sets or derivative data sets, the vectorized, say, data coming out of it. And that's all free. Now, the other thing I would say is same BYOD. Maybe you're an organization that has ArcGIS out there. I'm going to guess probably 100% of our attendees have ArcGIS, especially in the government space. So that also leads me to believe there's a good chance you're probably using field maps, Survey 123, Quick Capture, right? How are you doing that? Well, maybe you use a tablet or a phone, and you're already collecting that data, that GPS data, with a tablet or phone. You're already there. You have half the equipment. So my point here is your GIS system is already enabling you in some ways. The phone in your pocket is enabling you in some ways. If your organization used drones, so maybe you took the plunge 10 years ago into drones, and you've got Pix4D for photogrammetry for your drones, it's probably not a hard sell to go, why can't I do this on the ground? Why can't I try out catch? And so the connections are really there. And I would leave you with this, my shameless plug as a sponsor. Reach out to us, or I will reach out to you after this. We can send you a sample trial Flex for free. It comes with a return shipping label and a box. You can have Pix4D Catch as a trial. We'll give you a few minutes of training. I mean, and within a few days, you've got, again, actionable data sets. And, Tom mentioned utilities. Obviously, Tim showed a whole project site, but he also vaults and such. I mentioned ADA, but another great example would be like culverts, right? So we've got a lot of people go out, collect your data and field maps, your X, Y, and Z points, take a few pictures, get to the critical asset, minimize field maps, fire up Pix4D, collect your 3D scan, and with a little techno wizardry in the back end, you've now got all that data kind of together in a digital twin. So I think it's a lot easier than you may think. And there's a lot of people out there willing to help. So
Very nice. Tim, Nick, Tom, thank you. This has been a very informative hour and a half, learning more about this and learning how people can use this technology today, that it's approachable, that it's affordable in the utility space and many other sectors. And great to have you, and look forward to the next event. That will conclude this webinar. Thank you all.
Thank you.
thank you.